Chapter 2. Chapter 1, Chapter 2 are on exam 1. Next week, we'll come back for a review. And the basis of the review is the review document. Did I hand one out to you guys? Give you a review document to look at? Did I not give you one of those? I'll look, see if I've got any. The review documents are in Blackboard in the exam 1 module. And that they come in 3 flavors. There's the form. It looks just like an exam, and you can treat it like that. If you want to practice, you can run through it and then go back and check yourself. There's also a key that'll give you the answers. And then if you still don't understand some of the problems that you might be getting wrong, then I've got worked problems. That's a document where I hand wrote out solutions to most of the problems. If they were just pure memory or better explanation was in the book, then I reference chapter and section in the book to go look at that. But most of them I wrote out and solved the problems, so you can see this is one way to do it. In chemistry, most of the time, there's more than one way to solve a problem. So when we come back next week, we'll use that review document as our basis for review. So if you have any specific problems that you just can't work out any other way, then we'll tackle those first. And then once we've got everybody's problems satisfied, I'll go into a review spiel. I've got several of the problems picked out, and if we don't review any of them as particular problems for you, then I'll just go through them one by one. I'm not going to do all of them, of course, but because there's a lot of repetition in there. So I'll pick the ones that I think are relevant to help you with the exam. And if, of course, during the review, if we're talking about something and just something clicks back here and you just stop me, okay? And we'll tackle it. Because I got my document and that'll show me where I left off and I go back. So I don't have to rely on my memory, which is fading more and more as the years pass. Okay, so we're going to look at chapter 2. Chapter 1, we were more interested in general premises of sciences. Now we're going to get into some of the nuts and bolts of chemistry. And remember, I think I mentioned this, the key to the intuition that you want to develop over time with chemistry is to make a connection between what you can observe and what you don't see. Things underneath. The microscopic level is actually controlling what you see. And that's what we're going to talk about today, atoms, molecules, and ions. Okay, we can start off a little history lesson. The Greeks tried to explain, the ancient Greeks tried to explain why substances change from one thing to another. But they weren't very good experimentalists. They were more head people. So they were philosophical about it. So they figured if it adhered to what they had learned as kids, which they teach their kids young back then, rhetoric and logic. And in fact, when they taught them geometry, they didn't have pen and pen. Right? They might draw stuff on the ground, but then it was gone. So everything they learned was up here. So they relied on that more so than on experimentation. There were some experimentalists there, but the prevailing theory, the accepted explanation for how things change and what they're made of, had to do with the 4 basic elements, right? Earth, wind, fire, and water. Thank you. Earth, wind, fire, and water. But there were a few holdouts that said, nah, that doesn't make any sense. You know, you can't explain what you see with just those 4 elements. So we had these atomists, those who believed in the atomic theory. of their day. They believed that everything was made of the simplest particle, which was the atom. And they called it the atom because in Greek, that prefix means not. It's the opposite of whatever the root is. And the root here is tomos, which means cut or divide. So you can't divide it any further. That was the elementary particle, what they were describing, was the foundation for all matter. They were on the right track. The problem was, they said that everything you see is composed of the same atom. That elementary particle was the same for everything you see. And that led to some difficulties once they tried to apply that to the changes. It kind of fell apart. We'll talk about how that problem was solved later by John Dalton. But in the intervening millennia, we had alchemists, especially during the medieval period, were interested in, among other things, changing base metals into precious metals, like lead into gold. We hear that. But they were doing a lot of other stuff. Some of them were actually looking for the elixir of life. I think Isaac Newton was active in that one. And in the process, they discovered several elements. Right? They also knew how to prepare and use mineral acids. So mineral acid is like hydrochloric acid, sulfuric acid, nitric acid, because they use them to dissolve materials. So we had that basis to build on when modern chemistry rolled around. And the first modern chemist, we believe, we attribute to Robert Boyle. Right? You'll get a taste of Boyle when we start talking about gases. The first law we're going to investigate is Boyle's law, the relationship between pressure and volume. In fact, you've already been introduced to it if you've looked at the graphing lab. But he was the first one to perform quantitative experiments. He actually measured things in an experiment. Now, measurements had been developed up to this point, but nobody really used them to answer questions about physics or chemistry. And he developed the first practical definition of an element. I think the problem with the alchemists was they were very secretive. They're more like high-end chefs. I've got this recipe and I make this thing, no other restaurant has it. And the only one who knows about it is my apprentice. I pass it on to my apprentice and they carry on. As opposed to now, modern science is just the opposite. You get credit and your reputation is built upon publishing your results and arguing your point in referee journals and trying to convince as many people as possible of your position. But you make your experimentation available to everybody so that they can run your experiments and check your work. Okay, so in the early part of the middle part of the 18th century, Lavoisier, who was a Frenchman, also did some experimentation, and he concluded that during the chemical reaction, matter is not created and it's not destroyed, either one. You have the same mass of reactants as products during a chemical reaction. That's the law of conservation of mass. Remember, laws, you don't have to explain why they work. It just says, this is what happens. It's a descriptive expression of what happens. And then, well, Lavoisier, he was a pretty smart fella. He just made one mistake. Actually, it was a historical problem that he may not have seen coming. He bought a license from the king to collect taxes for it. Right? And in those days, if you collect taxes, you can collect a little more than the king wants, and you get to keep the extra. But whether he did that or not, nobody liked tax collectors. They didn't like them then. We don't like them now either. The problem was the French Revolution and the Reign of Terror and Dr. Guillotine created this device that supposedly was quick and painless. Just chop your head off like that. Well, Lavoisier lost his head. Then there came along Proust, who was another Frenchman. And he said that for any compound, and we haven't even defined compounds yet, have we? Right, for any compound, say you need 2 or more different elements combined as a single unit. So water would be a perfect example. Like you got hydrogen and oxygen combined together, and they act like a unit. They have a different identity than either of the elements from which they're derived. Proust said that his law of definite proportion said that this proportion by mass, that's all they knew then, was just mass ratios. They didn't know about numbers of atoms yet and how they combine. So this is our expression. They just knew that hydrogen and oxygen always combined to make water in a definite mass proportion, right? And it didn't matter where they came from. Right? This water could be from the combustion of hydrogen and oxygen to make water, or it could be from acid-base reaction. Right? We could take a base like sodium hydroxide and combine it with hydrochloric acid, and that yields table salt plus water. Proust said it doesn't matter. The mass ratio of these 2 elements are the same for this compound, no matter what the source. Or you could just physically purify water, distill it, and it would always be the same mass ratio. So that was the law of definite proportions. Now, teaser. Eventually, science is going to come up with an explanation of why these laws work. But for now, these fellows just said, this is what happens. Next on the agenda is the law of multiple proportions. And it was proposed by an Englishman, John Dalton. And he said when 2 elements come together as a compound and they form a homologous series, we call it. So you have only the 2 elements, but they're different compounds. Right? You know you only have those 2 elements, but they combine in different mass ratios. If you hold one of those constant, say you know what the mass percent of each one is for the different compounds, then if you ratio them such that one of them is held constant, say 1 gram, then the ratio would tell you that the other one would be so many grams. For instance, if we combine, I will start to keep that on. This might work. Nope. I have to go to my bag. Let's see. Yeah, nothing's in here. I probably have to prime it first. No more. I did this one time, forgot to put the cap on it. Slung ink everywhere. Let's start over. There. Nitrogen and oxygen can combine and make this compound. They can combine and make this compound. Now we know these are the ratios now. They didn't know that then. They didn't know that 1 atom of nitrogen and 1 atom of oxygen. They just knew the mass ratio. or we can make that. Well, now that we know the ratios, they've determined the ratios of these elements. If we hold this one at 1 gram, then we can calculate the mass of the others, right? I don't happen to know what that is, but whatever it is, X for this one, this mass is always going to be 2X, and this one's always going to be 3X. Okay. That's the law of multiple proportions. They are proportionate by whole numbers. 1, 2, 3. Okay. In fact, Dalton was on his way to proposing a theory that would explain all 3 of those laws. And I think that's what we got coming up. Yep. Dalton's atomic theory at the dawn of the 19th century. So when I look at the history of chemistry, actually the history of sciences, it amazes me what these people were able to accomplish when you look at the year, right? What was going on in 1800? Well, I'm no historian, but it was pretty primitive by our standards. And they still came up with this stuff. It just amazes me. So what Dalton's atomic theory says, these are the premises of his theory, right? The postulates, we might say. Each element is made up of tiny particles called atoms. We've seen that one before, right? So I suspect he stole that from the ancient Greeks. But he went a step further. He said, these atoms right here, for every different element, are identical to each other. Each element has its own atom. And the atoms of different elements are different. So that solved the problem that the ancient Greeks had of trying to explain how you get different things from the same kind of element, the same kind of atom. So that's what caused the difference in the elements. It's their atoms are different. Oops, skip one. Chemical compounds are formed when these atoms bond together in some form or fashion. He didn't explain how that happened. That came later. But when they combine, they form compounds that have different identities from their parent elements. Like oxygen supports combustion. Hydrogen is flammable, but water is neither. It's got a different identity. And he said, the reason for this, the reason for the way compounds come together is that each compound has the same relative numbers of atoms. So he's getting away from the shackles of mass only. Now he's talking about numbers of atoms. So that's why we write H2O, right? 2 hydrogen atoms and 1 oxygen atom. And each atom is different for each element. So the hydrogen atom weighs a certain amount, the oxygen atom weighs a certain amount, you combine them together and you get the mass of water, plus you can ratio the masses of the atoms, simply because they always combine in those definite proportions. Then he said, when substances come together and react, elements come together, or elements and compounds come together, whatever the case may be, the explanation for the law of conservation of mass is that all they do is just swap partners. They just rearrange. So if you rearrange the atoms, you haven't created any, you haven't destroyed any. You got the same number of atoms after as before. That explains Lavoisier's law of conservation of mass. Okay, we're not done yet. There's more history. These two fellows, Gay-Lussac was, I don't know if he was a contemporary, he might have been a little earlier than Avogadro, but they were I'm not sure about Gay-Lussac. He might have been French. I know Avogadro was Italian. But Gay-Lussac did work. He researched reactions between gases. And he measured the volumes of gases before and after reactions. And in order to do that, he sort of intuitively knew that you need to hold the temperature and pressure constant. They knew that 4 conditions describe the physical state of a gas: pressure, volume, temperature, and the number of particles. That's what my N stands for. Actually, it stands for moles, but we haven't defined moles yet. So if you know these 4 conditions, you can completely describe the state of a gas. And the reason for that is that gases tend to behave, except when you're invoking a chemical reaction, but the physical behavior of a gas is the same no matter what the gas is composed of. So what the element, what the compound, they all behave alike. So that's why, historically speaking, gases were the first state to be investigated by scientific means, by modern science. Because it didn't matter what the gas was. You could use air, you could use pure nitrogen, pure oxygen, didn't matter. They would still behave the same way based on these 4 conditions. So Gay-Lussac took these different gases and reacted them and noted the volume of the products. Now, he could also tell that they had the same mass before and after, right? So it obeyed that. But he also noticed that 1 plus 1 doesn't always equal 2. Right? Or in this case, 2 volumes of hydrogen and 1 volume of oxygen actually equals 2 volumes of water vapor. Okay, so how do you explain that? Well, he didn't. Gay-Lussac just noted these things. Now, sometimes they obeyed, right? 1 plus 1 equals 2 for hydrogen and chlorine, right? Where's the explanation? Well, the explanation for the first one was this 2 volumes is due to 2 of hydrogen. And 1 volume of oxygen is just 1 oxygen. Remember when from your periodic table, the ones I've put in those blue boxes, those are diatomic elements. Hydrogen is one of them. It's always this way at 1 atmosphere pressure and room temperature. And oxygen is always that way. Right, so when you react them, one of these oxygens takes 2 hydrogens, and the other oxygen takes the other 2 hydrogens. So 2 volumes of hydrogen are required here to react with 1 volume of oxygen. And then what do you get? Well, you actually get 2 volumes of water vapor. Okay? So this is our modern explanation for what Gay-Lussac was observing. But it took Avogadro to finally crack the puzzle. Let's see. Let's go back. Come on. Well, this is okay. It gives me more whiteboard to write on. Avogadro actually didn't flesh out his theory quite completely so that other scientists could understand what he was getting at. It took a student of his. His name was Catanzaro. Catanzaro. He was an Italian, and he didn't like the textbooks that were available of that day. He had been exposed to Avogadro's theories, and so he wrote his own. He was a teacher, also, among other things. So he decided he would just write his own textbook and his own lab manuals for his students. And he put that in a published form. Well, At this time, which was the mid 1800s, the chemical industry was starting to take off in Europe, particularly Germany. The problem was they only understood masses. How do you combine? They had recipes, a mass of this and a certain mass of that together, and you get a product, and you just clean it up, and then you can sell it, make money. Well, these industries were having huge problems with reactions that went bad. Sometimes the reactions didn't work, and they didn't know why. So, among other things, to solve that problem and to bring together scientists, big heads from universities and companies to solve other problems like, what do you mean by an atom? What do you mean by an element? What's the meaning of a compound? How do you define the molar mass? Well, actually, they didn't know molar mass. How do you define the mass of an atom or the mass of an element? At that time, they said oxygen, well, oxygen was the standard. So they said oxygen was exactly 16 grams. Or no, 16 atomic mass units, and everything else was related to that. Well, that was okay, but the problem was that oxygen existed as O2, so it was actually 32 grams. Well, they came together in a little town in southern Bavaria called Karlsruhe. There was a small college there, and they figured it's kind of out of the way, and Bavaria was nice that time of year. So they all came together, and they said, we're going to solve this problem right here and now. Well, they didn't. They threw up their hands and said, all right, you all go back to your labs and you decide individually what you want to do. Well, Cannizzaro attended that meeting, and he presented his new course that he was teaching his students. And he actually had reprints of his course available to hand out. So as the scientists were leaving the meeting in disgust, he was handing these things out to everybody. And they were distributed also to others who hadn't attended the meeting. So a couple of other German, Lothar Meyer and Dmitry Mendeleev, right? They were responsible for periodic table. They got hold of a copy of it too. And they actually used what they had learned. And the light bulbs, like light bulb over our head, just went on all over Europe. Everybody said, this is fantastic. This solves all our problems. So now I need to tell you what that solution was. Okay, so Avogadro had presented this to Cannizzaro, and Cannizzaro ran with it. He said that if you have a volume of gas here, that's not working 2 milliliters, is it? And a volume of gas here, those volumes are equal. Okay, so this volume is equal to that volume. And then they also knew, Gay-Lussac's work, that you needed to have pressure equal for each one, and temperature is equal for each one. If all of those conditions are equal for each one of those containers, then what also has to be true? The number of particles in this one has to be equal to the number of particles in that one. Because it doesn't matter what the gas is, like I said before, it just matters how many of them are there. So the same number of particles in this one as in that one. Well, if you've got the same gas in each one, if you had helium in this one and you had helium in this one, then the masses are going to be equal too. The mass of this one is equal to the mass of that. But instead of helium, let's put neon in here. Now, the mass of this one is greater than the mass of the other one. So, if you know that the same number of molecules or atoms are the same number in each one, how do you explain the difference in mass? It's because each atom of neon weighs more than helium does. So now you can ratio the number of particles in each one by their mass. Right, they're noble gases. That's why I used them, because they're always gases anyway. Well, until you compress them. You can produce liquid helium, which is really, really cold. So we now know that the molar mass of helium is 4 grams per mole. And I'll still have to define what a mole is, so just take my word for it. The same number of particles in this one weighs 4 grams. The same number over here would weigh 20 grams. So now you can get a ratio between the two. They're 5-to-1, right? Neon to helium. So now that you can ratio the masses and know that the numbers are equal, now you can fix the atomic mass for each element. And now that you know that the atomic mass is a certain amount for each element, you can relate that to how many particles there are. So if you have a different mass here, then after you've done the preliminary determination of their masses, then you can say, if you have a certain mass of this element that goes into a reaction, then you know how many particles that represents.
Isn't it like 6.23 times 10 to the 23rd, 26?
Close. Okay, a mole is simply a number of things. 6.022 times 10 to the 23rd. Now, for our purposes, that could be atoms, that could be molecules, that could be ions.
And like the numbers, isn't it the mass that's listed, like it's not the mass of like an atom, it's like the mass of one mole of the element.
The periodic table is set up. You can interpret it 2 different ways. You can say, if this one says, let's see, if neon says, well, they're different isotopes. We haven't talked about that yet. So let's say on average it's 20. That could either mean one of 2 things. It could be each atom is 20 atomic mass units, or if you have a mole of neon atoms, that mole will weigh 20 grams. Okay. We'll discuss that in a little more detail later. Okay, so now that problem has been solved. And then the industry was back on firm footing. And chemical industry in Germany just took off. For the longest time, I remember when I was high school age, if you wanted to go into chemistry, in high school, you studied German. If you wanted to go into the law or medicine, you studied Latin. Now, we don't do either. But you studied German to be in chemistry because most of the publications that were of value in chemistry were published in German journals. But it's kind of shifted over toward English now. So where even if it was published originally in some other language, they usually have translations of them now into English. And our English journals are translated also into other languages. So that's not such a big issue anymore. Okay, now we know we've gotten down to the level of the atom. So the identity of the element is determined by what atoms make up the element. And an element, a pure element, only has one type of element, one type of atom. Okay, is that identity. But that's not the end of the story, because at this point, an atom was just viewed as like a gumball. You don't know what's there. Is that as simple as you can get? Right. Well, by the time J.J. Thomson rolled around, actually it was before that, in the 1700s, electricity had been discovered. And Volta had made his pile, different metals, zinc and copper, and you could make a battery. And it was all the rage in the salons of Europe. Right? What you would do is come for a party and you'd have food and drink, and then you'd gather together for a little electricity. So you'd either have a battery or you'd have a servant winding a static charger. And everybody would hold hands, and then one on the end would touch that charge, and everybody in the line would jump. So that was how they had fun back then, some of them anyway. But they knew about electricity, and J.J. Thomson investigated the scientific angle of that. He had at his disposal what they called a cathode ray tube. It was basically just a long tube that was completely or partially evacuated. It had very few gas atoms left in it, but it had two plates, and you charge one negative and one positive. And he noted that with just a few gas molecules in there, you could see a stream from one to the other. You could see the cathode ray. So the cathode would emit particles that would end up at the anode. And he determined from his investigations that those were negatively charged particles. And he also determined by other experiments the ratio of the mass of that particle he called the electron, the ratio of the mass to the charge. He had not so much of modern science and its development is based upon technology. The technology wasn't there yet to determine the mass of the electron, but he was able to determine the charge to mass ratio. Well, he also said that these electrons come from any matter. It doesn't matter what he put in there for the plates. It produced the same stream of particles. So he knew that this was a particle that was common to all atoms. Well, that begs the question. We knew that elements were neutral. Unless you forced them to acquire a charge, they were neutral. And you knew they were neutral because you could create a electric field, and there was no movement. They didn't move either to positive or negative. So neutral atoms, there had to be a balancing positive charge somewhere in that atom. So he said, this is my model. This is my theory. I know that there are negative particles in here that I call the electrons. Right? Those electrons. It said, I don't know where the positive charge is coming from. So I'm just going to say there's an equal magnitude of positive charges in that atom, and it's kind of like a soup or a pudding. So we call it the plum pudding model, because we knew these particles were there, the electrons. They were like the raisins or the currants that are in your pudding. And then the positive charge is just the mass that holds the electrons together. Okay, that was his theory. And there's his cathode ray tube. This is a recreation, but you could also deconstruct it and put things inside of it. And I got a video coming up that'll explain that a little better than I can. There we go. Wrong one. Let me see if I can get the volume up a little bit. No. Let's go back.
rays are produced in a discharge tube. A vacuum pump is used to evacuate the discharge tube. The cathode of the tube is connected to the negative terminal of the battery, and the anode of the tube is connected to the positive terminal of the battery. It was observed that, at normal pressure, the gas did not allow the current to pass through it. However, when the pressure of the tube was reduced to 0.001 millimeter Hg, and a high potential difference between 10 kV and 20 kV was applied, at the end of the tube, a glow was seen on the walls of glass tube. The rays emitted by the cathode travel towards anode. The attraction of rays towards anode reveals that the rays carry negative charge. Properties of cathode rays are: 1. When any object is placed in the path of the cathode rays, these rays cast shadows. This shows that cathode rays travel in straight line. 2. When a wheel was placed in the path of cathode rays, the wheel rotates. This shows that rays consist of some particle and some kinetic energy. 3. In the presence of an electric field, the rays are deflected towards the positive plate. This confirms that cathode rays consist of negatively charged particles. 4. In the presence of a magnetic field, the rays are deflected. This shows that the cathode rays are affected by the magnetic field.
Okay. I hope the microphone picked that up too.
Cathode rays are produced in a discharge tube.
There. Okay. So, after J.J. Thomson's work, not too long after that, Robert Milliken, who was an American scientist, and at this time he was a professor at University of Chicago, and he was working on a number of things. The photoelectric effect was one of them, and he was also interested in this particle that J.J. Thomson had discovered. He knew that Thomson had published his work, and everybody knew the charge to mass ratio of the electron. Nobody knew how much the electron weighed. Well, I mean, what its mass was. So Milliken set about to figure that one out. And what he used was a device that he created. It was a vacuum chamber with some viewports in it. And of course, he needed a telescope so that he could look at the oil drops that he produced in this device. And the oil drops carried a charge. And by some stepwise calculations, he determined both the mass of the oil drops and the charge on each oil drop. And he repeated this experiment thousands of times. It's like he just wasn't satisfied. But eventually, he determined that both the charge on the electron and the mass of the electron was this amount, 10 to the minus 31 kilograms, which is pretty small. And he got a Nobel Prize for it, for his work with the electron and for experimental work with Einstein's photoelectric effect. Several years earlier, Einstein also got a Nobel Prize for his theoretical work on photoelectric effect. He mathematically explained the photoelectric effect. Everybody know what the photoelectric effect was? It's the same thing that drives photovoltaic cells. Okay. So when light strikes this material, it ejects electrons. And you can capture those electrons and make them do work for you. Okay, so Milliken determined, and I think the next video is an explanation of the oil drop experiment. I wish I could get more volume out of this thing. That's the best we can do. Yep, that's as far as it'll go.
In a series of experiments carried out between 1908 and 1917, R.A. Milliken succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Milliken was able to determine the mass of an oil drop from its terminal velocity. Next, Milliken used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Milliken could solve for Q, which is the charge on the drop. Milliken found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Milliken concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge to mass ratio of an electron determined by Thomson using a cathode ray tube, Milliken was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
No kidding. Okay. It is a small mass. And the only difference between the slide before that and the video was the units of measure. They reported in grams, and the previous slide was in kilograms. Okay. So we've got an atom that we know is composed of electrons and some positive charge, but we don't know the nature of the positive charge. We do now know the mass of the electron. And because we also know, based upon a series of experiments performed following Avogadro's law, that the mass of individual atoms is much, much larger than the electron. So the proton has to be a pretty massive amount. That is, eventually the positive charge was identified as a proton, and the mass of the atom had to be accounted for by that other particle. So we needed some developments to take place before this bit of information could be extracted. And we needed work on radioactivity. Henry Becquerel, well, he was French, so we pronounce that Henri, characterized radiation in one of three different forms. It could either be gamma rays, which are very just high energy light beams, or it could be particles. Beta particles were identified as equivalent to electrons in both mass and charge. It's just that they were moving really fast. And then there were alpha particles. By comparison to beta particles, alpha particles are massive, and they turned out to be the nucleus of the helium atom. Okay, so now we have these, and we knew the types of radioactive elements that would produce these particles. So you could pick and choose. If you could find a pure element that produced the type of particle you wanted, then you could use it in experiments because now it had been characterized. So that's what Ernest Rutherford did. He was an Englishman. And so he decided that plum pudding model just didn't do it for him. He said there had to be particles in there. And if these particles were really massive, then where were they located? Were they just scattered in space? He said that doesn't make sense to me. So this is where the guesswork comes in, creating your hypothesis. Rutherford said that his hypothesis was these positively charged, massive subatomic particles that were eventually called protons were located in the center of the atom, in what he called the nucleus. And the electrons were out here in space. So his nuclear atom would be a very tiny, but very dense part of the atom where the protons are located. And then the electrons are out here. That thing's not working very well, is it? So what he needed to do now was devise an experiment that he could test his and determine is my explanation accurate or is the plum pudding model accurate? So that's where he came up with his gold foil experiment. And he used alpha particle emitters as probes in the gold foil. So why did he use gold foil? Well, first of all, he was going to fire alpha particles at the gold foil. The gold foil was going to be his target. And then he had detectors placed around it. And he said, if the plum pudding model is accurate, then these alpha particles fired at the plum pudding model in a beam would come out and they'd all be over here, because they knew that there was a lot of mass in the atom that wasn't accounted for. And if it was spread out like that, then all it would do is just maybe slow these alpha particles down, but it wouldn't change their direction. And they'd all end up in a spot over here on a detector. But if the nuclear model is correct, then most of them would go through, right? Because the electrons out here have very little mass, they wouldn't slow them down. So most of them would be over here in a bright spot, but occasionally one of them would bounce off the nucleus. Sometimes it would hit it, and it was so massive, it would deflect this way. But if it hit right head on, it would go backwards. So that's what he was looking for with his detectors. Now, why did he use gold foil? Well, two reasons. They knew how to make very thin layers, a very thin gold. It could be hammered down to just a few atoms thick. So the Capitol Dome in Charleston is just a few ounces of gold. It didn't take much. So most of the cost of that was the installation. So he could have just a few atoms thick. He didn't want a lot of atoms in the target, because if he had a lot of atoms, then the beam would just be stopped. I mean, there'd be so many atoms in there, the beam would never get through. So maybe 3 or 4 atomicals at that gold foil, and they would either go straight through or deflect. Okay, so the next video is I just said. Actually, there's no audio with this one. So there you have your alpha source. Let's see, can I pause it? Yeah. So this is basically a lead box with a hole on one side. So the alpha particles can only come out of one side, but they're going to come out like that, go in every direction. So what you need is a narrow beam. So that's why you put a slit here and a slit there, and only the ones that are traveling straight will make it through both of the slits in these targets. If you only had one, they could come at an angle and make a beam. I mean, a funnel instead of a beam. So if you have two slits, that's called a collimation. You collimate your beam, make it straight, and then it passes through this tiny slit here, and these are all the detectors. Let's see, in those days, probably used film as the detectors. So the film would be, they knew that radiation could expose film that was enclosed, right? Light can't get to it. And then there's the gold foil target. Okay, so let's continue. So on the atomic level, that's what we're looking at. Nucleus in the middle. These are all electrons. Another good thing about that gold foil was the gold atom is massive. It is huge. So it's going to have a big nucleus. It gives you a nice big billiard ball. Actually, you're firing marbles at a bowling ball, something like that. So let's see, let's go to the next slide. There we go. All right, so now we know that the atom is made up of electrons, the negative charge, and the protons, most of the mass, and the positive charge in the atom. The problem was the protons, the electrons are almost weightless when it comes to the mass of the atom. But the protons didn't have enough mass to explain the total mass of the atom. We needed another particle, something else to account for the rest of the mass. And we knew it could not be charged because we'd already accounted for the charges, electrons and protons. So it had to be a neutral particle. And one of Rutherford's students and later research associates was Chadwick, James Chadwick. And he continued to work as Rutherford's graduate student and then beyond. And received the Nobel Prize for his discovery of the neutron. So we don't have time to go into that experiment, but it satisfied the Nobel Prize Committee. And so he got his, actually, that was pretty quick. If he did his work in 32 and got a Nobel Prize in 35, that is blazing fast for the Nobel Committee. It usually takes them 10 or 20 years to make up their mind. Okay, so now we know that the nuclear atom, Rutherford's nuclear atom was the way to go. That's how the atom is constructed. With a small nucleus, it's very dense and has protons and neutrons in it. And then everything else, the negative charge is electrons in this space around it. So now we're starting to get a picture of the atom. And when atoms come together and react, we relate this back to chemistry. When they come together and react, what do they see first? They see electrons. So we're starting to get a feel for the bonding between atoms is due to electron interactions. Doesn't have anything directly to do with the nucleus. It has indirectly to do with the nucleus because, right, the number and behavior of electrons is based upon what's in the nucleus, but the chemistry takes place with the electrons. Right? So there's a relative, the nucleus roughly is on the order of 10 to the minus 13 centimeters, but the size of the atom is 10 to the minus 8 in the general area. So that's 5 orders of magnitude difference. Right? So you can safely say that atoms are mostly empty space. Okay. Now, remember Dalton's atomic theory. He said that all the atoms of a given element are identical. Well, as far as he knew, they were. And their chemistry is so similar that we can treat them all the same. But they're not identical, because now we know that some atoms have a certain number of neutrons of that element, and some have more or less neutrons, fewer neutrons. Get my English correct. So that brings up the topic of isotopes. So how do we define an element now? We define an element by the number of protons. If you change the number of protons, you have a different element. Okay, so if the mass is going to change, we've got to do it with neutrons. And we do know that the mass of different atoms of elements can be different. They can be isotopes. And that's the difference. The number of neutrons makes the different isotope. Here's an example, sodium. All right, this brings up, okay, we're using a notation here that we haven't described yet. So let me go back and get a whiter board here. Here we go. Let's say that this is the symbol for your element. Right? I use that because there's no element in the periodic table that has just an X. The only candidate is xenon, and it's Xe. So this is my generic element symbol. There are 4 positions here that are reserved for information. This position up here is reserved for charge. So it can be plus or minus or 2 plus or 2 minus, whatever the case may be. Down here is for the number of atoms. So if it's in a compound, you want to say how many atoms there are. That's where you put the number. Or if it's an element and it's diatomic, or sulfur is octatomic. Some allotropes of sulfur are S8. On the other side, this is the nuclear side. So on this side, we have designated by Z is the atomic number of protons. And then this one, designated by the letter A, is the mass number. So this references single atoms. A single atom combine the number of protons and the number of neutrons will be in this position. So if we're describing the isotopes of uranium, right, when they tried to separate the fissionable isotope of uranium so they can make a bomb back in the Manhattan Project, they were looking for this one, U-235. But most of uranium is this isotope, 238, and it won't fission. So if you're going to make nuclear power for peaceful purposes, you need to enrich the uranium up to maybe 5% is common. If you want to make a bomb, you got to go to 95% or greater. So that's what Iran is doing with their gas centrifuges. They're trying to purify uranium to a point where they can make a bomb, put it on a missile, threaten the world. But those two numbers are the total of protons and neutrons. So if we have, if A equals 235 and Z equals 92 for uranium, then the number of neutrons is simply the the difference of that. Okay. All right, so now we can go to that next slide and the isotope. The way they write the isotopes will have more meaning. So we have 11 protons for sodium, right? If you know the symbol, you know the number of protons. Or if you know the number of protons, you know the element and its symbol. Either way. So for chemistry, most often we don't even write these in here. For chemistry, we just stick to the right-hand side of the symbol. Okay, so there it is on a slide, except they left off the other two positions. Okay, so let's see if we understand what's going on here. A certain isotope contains 23 protons and 28 neutrons. What's the mass number? Well, add them together, right? 51. What's the element? We know the number of protons, don't we? So we know 23 protons, we have to go to the periodic table. So the periodic table is arranged from left to right and top to bottom. So the atomic number increases this way and it increases that way. So we just follow along until we find 23. It's right in here somewhere. Vanadium. So that's vanadium. Okay. That brings up let me see. I don't want to steal my own thunder. Are we going to talk about it in a second? Oh, matter of fact, no. Okay, so I better describe. How do we make an ion? An ion is an atom that has a charge on it, right? So how does it get that charge? Right? It's the balance of positives and negatives, right? If it's neutral, we've got the same number of, let's see, we have 23 protons. So we have, if it's neutral, we have 23 electrons. Okay? So how do you get a charge out of that? You need to change the balance, right? You need more positives than negatives for a positive ion and more negatives than positives for a negative ion, right? Yeah. So we can't touch the protons, right? Otherwise, we've got a different element. So it all depends upon how many electrons are there. For metals, usually they lose electrons and make positive ions. So if we lost, well, let me see.
Isn't it how when I don't remember what the process is called, but like the ones on
The non-metals?
no, the like the ones on the leftmost side, it's like
The alkali metals?
no.
Alkaline
This is
earth?
what I'm saying, the groups, I remember this from
Yeah.
PE chemistry, that it's like, these are +1,
Right,
these are +2.
right.
These are +3, these are plus or -4.
Right.
This is
Start from
-4.
this side now. -1, -2.
Yeah.
That's
I
right.
remember that.
That's right. Some of the groups produce fixed charges in their ions. That's what we're getting at here. Okay, so how do we do it? Well, I'm not sure what vanadium is, what its preferred charge is. It has several because it's one of the transition elements, and they have several possibilities.
It's always my least favorite part of chemistry. The fact that all the metals, you have like copper 3, copper 4, copper 2, like, and you have all the different ones up, and there's all the metals can be like all the different charges, and I hated it.
We're going to talk about that when we name compounds. Okay. Okay, so if we're going to make a charge here, we've got to change the number of electrons. And since it's a metal, we probably lose 1 or 2. Let's just say we lose 2. If we lose 2 electrons, the balance now is 2 positives. We're in excess by 2 positives. So that would be your vanadium ion. It's based upon the number of electrons that come and go and the balance. All right. So let's talk about bonding. We basically got two types of bonding. Now, this is for, if I hadn't said it before, I'll say it again. Nature just does what it does, right? And it's our job to catch up with it, try to figure it out. So one of the ways we do that is when we talk about bonds, we classify them as either covalent or ionic. Ionic bonds are easy to understand. You just get one positive ion, one or more, coming together with one or more negative ions, and they attract electrostatically. That's it. Real simple. So sodium, let's say it's sodium metal, solid, and chlorine, gas, yields what? Well, we know it's going to make table salt. All right, but I'm going to do something that we haven't learned yet. I'm going to balance this equation. Okay. Now, what happens? Well, sodium likes to give up its electrons, and chlorine likes to accept them. So we transfer electrons over here. Actually, we transfer 2 electrons, one from each of these sodiums, and each chlorine accepts the electrons. Now we have this one is a positive charge and that was a negative charge. That's an ionic compound. Okay. And this always happens between a metal and a non-metal. So on your periodic table, those on the left-hand side will be the positive, the cations. Those on the right-hand side would be right of that squiggle line would be the non-metals. That would be the anions. Okay, but if we try to form a compound between 2 non-metals, they have such a strong attraction for electrons that they won't give them up. So they settle on sharing. And we'll eventually talk about why they share. Those are the covalent bonds, where you share electrons.
No, what about the electron levels? Is that what that is?
But, well, yeah, the energy levels.
Energy levels.
Yeah, we'll get there. Now, this sharing occurs, sometimes it occurs equally, sometimes it doesn't occur equally. Maybe it's only partially shared. It just depends on how, which one in this tug of war is a stronger attractor for electrons. Now, they're not strong enough to completely strip the electron from the other one, but they can cause the electrons to spend more time in their neighborhood. Okay, so you have a range of covalent bonds. Sometimes they're perfect, like if you have 2 nitrogens together. And that would be, we're going to learn how to do this. This is a Lewis dot structure. These are 3 bonds, and these are lone pair electrons. But since this nitrogen and this nitrogen are exactly equal in their behavior, then this covalent bond is equally shared. The electrons are equally shared between the 2. That's a perfect, we call it non-polar covalent bond. All right. All right, so I've already described this, and I use 2 terms here that I haven't defined. Cations are the positive ions, anions are the negative ions. Oops. Oh, I got a video coming. I think I went too far.
So this is a video that addresses the question that students often have. What is the difference between a formula unit and a molecular formula? And that brings up a couple of questions itself. What are the structural differences between ionic and molecular compounds? And how do those differences affect their chemical formulas? So the chemical formula for a covalent compound is a molecular formula.
I'm going to try something. Hold on just a second. I've adjusted the volume all I can right now with the slideshow running. I'm going to stop the slideshow and see if I can do anything else with volume. Then I'll restart the slideshow.
So this is a video that addresses the question that students often have. What is the difference between a formula unit and a molecular formula? And that brings up a couple of questions itself. What are the structural differences between ionic and molecular compounds? And how do those differences affect their chemical?
I'm sorry.
Can I sit here?
You can sit anywhere you want to. Yeah. If it's more comfortable, sure. It's probably a little bigger than these other narrow seats. I could say something, but I'm not. Oops. Let's start over again.
So this is a video that addresses the question that students often have. What is the difference between a formula unit and a molecular formula? And that brings up a couple of questions itself. What are the structural differences between ionic and molecular compounds? And how do those differences affect their chemical formulas? So the chemical formula for a covalent compound is a molecular formula. And the chemical formula for an ionic compound is called a formula unit. So an example of a molecular formula, H2O, which is water, and for a formula unit, NaCl, the formula unit of common table salt. So what's the diff? And if we look at the structure visually, I think we can see very much what the difference is. So let's first look at sodium chloride. This will be our example ionic compound. NaCl does not exist as a single unit, like a molecule. This goes for all ionic compounds. So this would not be a valid way to represent sodium chloride. And like any ionic compound, in the solid state, sodium chloride exists as a crystal. So a very, 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 very tiny crystal would look like this with alternating sodium and chloride, and a little bit of a different view. The formula unit is NaCl, but if we look inside the crystal, the sodium and chloride ions are actually bonded to 6 oppositely charged neighbors. So if we shrink the ions, we can take a better look inside. And it's a little bit hard to see. So what we're going to do is take a look at a particular chloride ion, that one right there, and ask the question, how many sodium ions is the chloride ion close enough to bond with? Start with the head-on view first. And as we change the perspective, you can see there are exactly 6 sodium ions that the chloride ions is equidistant and can bond to. If we ask the same question of sodium, how many chloride ions can it bond to? Well, again, there are 6 chloride ions that it's equidistant to, and therefore the sodium ion also bonds to 6 chloride ions. So as you go throughout the crystal, you can see that is always the case. Because each sodium is bonded to more than 1 chloride ion, and each chloride ion is bonded to more than 1 sodium ion, then you can think of all the ions in the whole crystal part of one single bonded unit. And the crystal below would be Na32Cl32. So you can imagine that would be very impractical given the enormous numbers of ions in a crystal large enough to see with our eyes. So only the ratio of ions is given, and that would be its empirical formula. But we call the empirical formula of an ionic compound the formula unit. And sodium chloride is the formula unit for the sodium chloride crystal, and it is the smallest whole number ratio of sodium and chloride ions in the crystal. So all formula units are the smallest whole number ratio of the ions in the crystal. That goes for all formula units. Here's another example, calcium fluoride. You've got 1 calcium for every 2 fluorides. The calcium is 2+, the fluoride is 1-. It has a slightly different crystal structure to account for, rather than the 1-to-1 ratio of sodium chloride, you have a 1-to-2 ratio of calcium fluoride. And if we shrink the atoms to take a better look and see how the calcium is connected to the fluorides, you can see that each calcium has 8 nearest fluoride neighbors. And so it is equally bonded to those 8 fluoride neighbors. And if we look at the fluorine, each fluoride has 4 closest calcium neighbors. And again, like sodium chloride, the whole crystal acts as one single bonded unit. And so we need to express the formula as the lowest whole number ratio being CaF2. So what about molecules? How are they different? Let's take a look at water. We've got the space filling model on the left, ball and stick model on the right. It's covalently bonded hydrogen and oxygen. And a collection of water molecules is just that, a collection of individual units of H2O that are covalently bonded single units of 2 hydrogens and 1 oxygen. They're not connected to each other except by weak forces. And so large amounts of H2O and the interaction between the water molecules due to weak forces, the molecules behave, they still behave as individual units, not one large bonded unit as in an ionic crystal. Another view of water, here the hydrogens are white instead of yellow. And this I'm showing you to contrast more specifically with the sodium chloride or the calcium fluoride, because we showed the ionic crystals as solids, and here's water as a solid, ice, of course. And here, like ionic compounds, molecular compounds also form crystals in the solid state, a very ordered structure that you can see here. If we take a closer look, however, we can see that each H2O remains as a single unit and is not covalently bonded to any other H2O. The attractions that hold them in place are, of course, the very, very strong dipole, the hydrogen bonding that occurs between the hydrogen and the oxygen. But that is much, much, much weaker than the covalent bond between the hydrogen and the oxygen. And the H2O, therefore, remains a single unit. So we look at these structural differences between molecules and ionic compounds by how we express them in their formulas. Molecules represented by a molecular formula showing all the atoms present in the unit. The ionic compound is represented by the ratio of its ions, and that is called a formula unit. So here's the H2O molecule, and here versus the NaCl formula unit. Many sodiums and many chlorides, yet it's still just expressed as the lowest whole number ratio. It's 1 sodium to 1 chloride. In summary, in a molecule, the atoms given by the formula are covalently bonded. In a collection of those molecules are attracted to each other by weak forces, but no covalent bonds occur between the molecules. The molecules exist as individual units of covalently bonded atoms. But in an ionic compound, where the bond is the electrostatic attraction between oppositely charged ions, each ion is bonded to each of its oppositely charged neighbors. So for any ionic compound, all the ions in the whole crystal can be thought of as part of one single bonded unit. So the formula unit shows the lowest whole number ratio of the ions, rather than representing very awkwardly all the ions in the crystal, which in most cases would be impossible to determine anyway. So that is the difference between a formula unit and a molecular formula.
Okay. It took a while to explain, but I think that was a good video. Those forces that the narrator was describing that hold molecular substances together, like water, we're going to talk about those next semester. You come back. That's for 102 chemistry. In fact, that's where we start. We call them intermolecular forces. But if you want to know the relationship of the strength of bonds, the strongest bonds on average are the covalents. These are the strongest bonds. The next strongest bonds are the ionic. And then you have the weaker bonds, which are the intermolecular forces that I was talking about before. So we probably won't talk about those until next semester. Well, let's get back to the structure of atoms. If we have, say we know that the charge on this isotope is 1+. And we also know that it contains 54 electrons and 78 neutrons. So what's the mass number of this isotope? You look at it this way. Where did that positive come from? The positive came from the summation of protons, electrons, right? If you've got one extra proton versus electron, then if you've got 54 electrons, how many protons do you have? 5. Okay, so 55 plus 78 would be 133. Should be the mass number for that isotope. Okay, and we can tell based upon the number of protons we've determined here, 55, we can find out what element that is. We just have to follow along to find 55. There it is, cesium. Okay. So let's go back to John Dalton and see if we can knock him off his pedestal. His atomic theory made those postulates. Now, which one of those postulates is still true? Elements are made of tiny particles called atoms. Yep, I think that's still true. All atoms of a given element are identical. Nope, not anymore. We know about isotopes. All given compounds, a given compound always has the same relative number of numbers and types of atoms. Yes, that's still true. Definite proportions. And atoms are indestructible. Nope, we know about radioactivity now. Sometimes they self-destruct, and sometimes we're able to cause them to destruct. Fission and fusion, yep. Okay, so we know that those two postulates are still true. Now let's look at the periodic table and divide it up and start to understand how the periodic table is structured. So we look at a general division between metals and nonmetals. And while you're doing that extra credit, one of the questions was, draw a line in there that divides the two. So you got to go look for it, find it. And on this one, I think it's, this one doesn't have one. It starts right here underneath the boron, between boron and aluminum, and then it stair steps. And like that, like that, like that. Just keeps going like that. Over one down, over one down. That's the division between metals on the left, non-metals on the right. The table is also divided into groups. We used to call them families. But groups are the verticals. These elements are grouped that way because they have similar chemistry. They behave similarly. They're not exactly the same, but they're similar. And in fact, that's the way Mendeleev identified them. When he built his periodic table, he grouped elements by their chemical behavior and other factors. And he put them in his table is 90 degrees rotated. The first time he published, the second time he published it, groups were vertical now. And he put them in there based upon their characteristics, chemical and physical characteristics. And what he noticed was that when he came to the mass relationships, he knew that the masses were increasing as you go down. He noticed that if he followed along the periods, which are the horizontal rows of elements, then he would have to put an element in the wrong group based upon its behavior. So he said, it can't be, right? That can't go there. So I'm going to move it over here and put it in this group. And there's an element there that we're going to discover one of these days that will fit that position. And he actually went so far as to say, all right, it's going to have this mass and it's going to have these characteristics. And when he published his table, that's what he said. His table has a predictive quality about it. That's why Mendeleev gets credit for the periodic table, because he used it to predict the existence of elements that hadn't been discovered yet. Okay, so those are groups. And some of those groups have names. I think that comes in subsequent slide. Yeah, we'll talk about those in a second. But what are the periods? Well, if you know anything, if you've had any physics, you understand the concept of periodic motion. Right? When I think periodic motion, I think pendulum. Right? It's a motion that takes the object through space and then returns to a position at some point in time. And then it repeats. So think of that when you look at these rows, the periods. These elements have similar characteristics. If you go down here, they change in their characteristics as you go from left to right. And then when you get down here, if you go to the next heaviest element, wait a minute, that one's got the same characteristics as this group over here. That's the end of your period. That's the end of your motion. You got to swing back to the other side, start over again. So that's why they're called periods. Okay, all right, here's our dividing line, metals and nonmetals. And some of them have names. The groups have names. The first group is alkali metals. Second group is alkaline earths. And on the other side, you have noble gases. Then this group is halogens, right? And the next one to it is they're called chalcogens, named after compounds that are formed from oxygens. They call them calcs. And then these are pnictogens, starts with a P. The P is silent. And then the carbon group and the boron group, they don't have special names. Then all of these in here, between these two, these two groups and these groups over here are called representative elements. And then these in here that makes the transition between this side and that side are transition elements. Okay? And then these have names also. These are the lanthanides, simply because the first one in the group is lanthanum. And these are actinides because the first one in that group is actinium. But eventually we're going to understand why the periodic table is arranged this way. It has to do with the electronic structure of atoms. So once you start drawing the electronic structure of atoms, we can use the periodic table to do that. If you know where the element is in here, you can write its electronic structure. Oh, by the way, left out another one. The elements that occur close to this line, sometimes they behave like metals in some circumstances, and sometimes they behave like nonmetals on either side of that line. That's why they're called metalloids. But that's not a definitive group. In other words, some published works will say, this is a metalloid, and that's a metalloid, and that's a metalloid, but this one's not, and that one's not, and that one's not. So it's kind of operationally defined. But in general, on either side, we have the potential for metalloids. I wouldn't call aluminum a metalloid, because aluminum behaves like a metal all the time. Okay. Other characteristics of these groups is some of them have fixed charges. Right? So let's go back to the table. This group right here, when they form ions, they always form +1 ions, 1+ charge. This group always forms 2+ charges. Okay, now we're talking about ionic compounds. And you can say that about the metals. That's all they do. Well, there is a metallic bond, but we're not going to talk about that right now. So these form +1, +2, and then if you go on the other side, noble gases don't play with anybody unless you force them. Right? Some of these krypton and xenon, we force them to play with fluorine and some other elements. But in general, they have 0 charge. They never form ions. Whereas the halogens always form -1 when they're in ionic compounds. Right? Remember I said nonmetals can form covalent compounds. They can share electrons. When they share electrons, then they're not ions. Right? But when they're ions, formed compounds with metals, they prefer -1 charge. These prefer -2 charge, the chalcogens. The nicogens prefer +1 charge, +3 charge, -3 charge. Let me say that again. The nicogens are -3 charge in ionic compounds. And then the boron group down to about indium, they always form +3 ions. And then carbon group, carbon, silicon, germanium, tin, they tend to form, well, not so much tin. Germanium maybe. They can either be +4 or -4. It depends on what they're bonded with. You know about carbides? You know, carbide drill bit? Okay, they're made of metals that are bonded with carbon. When they do that, carbon is a -4 charge. And those carbides are extremely hard. They're ionic, but they're very hard. They're almost as hard as diamonds, some of them. And they're a lot cheaper to make too. That's why they're commercially available. Okay. So it's important to recognize that some of these have fixed charges, because when we start naming compounds, that's going to come into play. Which is right now. Does anybody need a break before we get into this? I do. So we're going to take a short break and we'll come back to naming compounds, and that should finish the chapter. Yep. Okay, so I'll be right back. I'm going to just let that thing run, because if I pause it, I probably won't start it again, and that'll just mess everything up.
Stuff I learned. Yeah, this is just like pretty. And kind of what we learned in introduction. But in math, it's terrible because, you know, I took college algebra. Last year I took AP calculus, which is a higher level class than the one I'm taking right now. Just getting a whole lot of review. Yeah, like right now we're relearning how to do factoring. Oh, like, you know, I went from all the derivatives to, you know, let's factor polynomials. At least you know you all do that. Yeah. That's all. I mean, it's a good start to college anyway. Because it's a pain in the butt sometimes.
Clock needs battery. This one doesn't rotate. That's good. Makes me feel like I was not as old as that.
I noticed it on the hallway too, though. It's like, I really don't think it's something since then.
No, that one I can't do anything about.
That's not on here.
But this one, it's better.
Really.
Maybe so. Hold on. Oh, I see the problem with that.
Yeah.
There it goes. All right. Okay, let's pick this thing up again. We learn how to name compounds. So once you've learned the symbols, you gotta know how to put them together in such a way that we can understand each other. If I say sodium chloride, you can immediately write that up here. Or if I say, dinitrogen tetroxide, you can write that one up there too. Or if I give you a formula, I say, potassium phosphate. You can name it. So you go backwards and forwards between writing the correct formula or naming the compound. All right. The convention we're going to start off with is the simplest, but all compound naming is controlled by this group, the International Union of Pure and Applied Chemists, or some subcommittee of that group that names compounds. This is called the binary method. So we name compounds as if there are only two parts to them. Now, the authors of the textbook and the slides say they're composed of two elements, but actually they're composed of two parts. Yeah, in the beginning, we're just elements, but sometimes those parts, either the first part or the second part, can be a polyatomic first, and then we'll complicate it with polyatomics. So binary compounds have two parts. They can either be ionic or covalent. We've learned that so far. So in the beginning, we're going to start off by naming ionic compounds. And then we're going to use that to help us with naming covalent compounds. All right. So the type 1 compound. In the type 1 compound, you have a metal and a non-metal. Okay. So you know where they come from on the periodic table. The key to this one is, does that metal have a fixed charge or can it vary? Right. And once the compounds form, the charge won't vary. But before it forms, it could be one or more, it could be two or more different charges. We're going to save that one. For this type 1, that can only be one charge. So that means it's got to be an alkaline metal, an alkaline earth, or the boron group. +1, +2, or +3. And when you put them together, you always put them together metal first, and you just name the metal. Like for sodium, you just say sodium. And if it's part of a compound, you recognize it as the sodium ion, not the sodium metal. It's not neutral, it's charged. And it has a fixed charge. Sodium's an alkali metal, so it's going to be a +1 charge. The non-metal, the anion could be anything. So it could have different charges. Since we know that the compound is neutral, if we know this charge and we know how many of the non-metal is there, we can deduce the charge on the non-metal. So the non-metal could be more than one charge, but more than likely it's not, it's a single charge. Like the halogens are always going to be -1 in this environment. Chalcogens are always going to be -2. Then when we put the element in here for this position, we change the ending to IDE. Right? So if it's derived from chlorine, we will say it's chloride. And if it's combined with sodium, sodium chloride is the name of this compound. Now, how do we know that's the correct ratio? Because this is a +1 and this is a -1. Okay, that makes it neutral. What if instead we combine sodium with oxygen? Sodium is still +1, but oxygen is a chalcogen. we say oxide. Right? Oxide, which means here. And if oxide is always 2 minus, that means we need 2 of those. Right? And when you write the compound, you don't put the charges in there. I just put them in there for bookkeeping purposes. So that's sodium oxide. And you only have to say sodium oxide, and you know it's this compound. That's another condition for that IUPAC imposed on writing and naming compounds is simple, non-redundant. In other words, if you say this, it can't be anything but that. Or if you write that, it has to be this. Right? It can't be anything else. Actually, the term I should have used was non-ambiguous. Right? It can't be multiple possibilities in either direction. Okay. That's a type 1. Oh, examples, okay. Potassium chloride, right? That's an alkaline metal. It's always +1. Halogens are always -1. So that's how we would name it, potassium chloride. Magnesium is alkaline earth. It's always 2+. And bromine is a halogen, -1. So we know that it's the ratio here. Remember that video? These are formula units because these are all ionic compounds. The formula unit here is 1 magnesium and 2 bromines as ions. So it would be magnesium bromide, and that's all we have to say. We don't have to say how many there are. We don't have to say what the charge is because the charges are fixed. Calcium oxide. Calcium is an alkaline earth, 2+ charge. Oxygen is a chalcogen, -2 charge. So you only need 1 of each to have a neutral compound. And calcium oxide is unambiguous. That is its name and its formula. Nothing else is possible. Type 2 compounds. Now we start to muddy the water a little bit. The metal, we're still a metal nonmetal. Now the metal could have 2 or more possible charges. Okay, it's still going to be an ion, but we don't know what the charge is until we actually say what it is. So if you're given a formula, then you can deduce from the formula what the charge is. And if we say, for instance, if we have this one, iron and oxygen, and this one is 3 and this one's 2, then what do we know? We know this one is always 2 minus. Right? So that means how many minuses are in that compound? 3 times 2 is 6 minuses. So we got 6 minuses here. Has to be balanced by 6 pluses. So 6 pluses over here, distributed evenly between the 2 irons, means that this iron is 3+ charge. Now that we know the charge on the iron, we can write the compound. So we just say iron, oxide, and we say what the charge is with Roman numerals. Roman numeral 3 says that iron has a 3+ charge. That's how we're unambiguous with our naming for that compound. And you can take this name and write that compound. Just follow the logic and go backwards. Most of the metal atoms that produce these variable charges are in the transition metals. Not all of them, most of them.
Isn't silver one that's always the same?
Yes, there are exceptions. Silver is always a +1. Copper is always a +2. And zinc is always a +2. Right? So you can treat those as type 1s because they're fixed charges. So we can say silver chloride. That's all you have to say. Silver is a 1+ charge, chlorine is -1 charge. There'll be an AgCl. The rest of them, they're not representative groups. They can have set different charges. Like lead can have a +2 or +4 charge. Tin can have a +2 or a +4 charge. In that case, you have to specify the charge with a Roman numeral when you write the name. Okay, those are type 2 compounds. Let's see, copper. Oh, yeah. I misspoke. Copper can have more than one charge. It can be a +1 or sorry. Silver can only be +1 and zinc can only be +2. Well, it is, right? Going back to my original premise, nature does what it does and we have to follow. So zinc, in every instance we've seen it, is always +2 charge. So copper can be 1 or 2, so we have to say, what is it? Well, in this case, bromine is a -1 charge and there's only one of them. So copper has to be a +1. Sulfur is in the chalcogen group, it's a 2-, so iron has to be a 2+. So if there's only one of each, that logic has it. Here we have chalcogen, oxygen, with a 2- and you got 2 of them. So there's 4 minuses that have to be balanced, but you've only got 1 lead. So it has to be a +4 charge. Now for the polyatomics. What do you do with the polyatomics? I gave you a list of polyatomics. Okay. The reason I gave you that list is because that's too many to memorize. If you use them over and over again, you'll figure it out. The easiest one in there is the only positive one in the group. This one. It's always right, ammonium. And when you use a polyatomic in a compound, the name is fixed. You don't have to modify the name. This is always hydroxide. This is always nitrate. This is always sulfate, polyatomic. And they have a fixed charge. This is a -1, and this is a -1, and this is a -2. And so those polyatomics, they don't vary. They always have that charge and that formula. Okay.
But I wasn't good at it, but everybody else did, but I didn't.
And polyatomics can be part of a type 1 or a type 2. This is going to be a type 1, right? Because ammonium is a +1 charge only, nothing else ever. So that means since it occupies the cation position, it fits into type 1. So here we have a polyatomic and bonded with another polyatomic. So how do we name that? Well, ammonium sulfate. And you don't have to say what the charge is. That would be redundant because the charge is always +1. So 2 of these matches 1 of those with a 2- charge and you're neutral. Whereas magnesium is a 2+ charge and nitrate is a -1 charge. So you need 2 of them. And notice when you need more than 1 polyatomic ion, you can't change the subscripts of the polyatomic. If you need more than 1, use parentheses because those polyatomics are covalently bound ions. They behave as single units. And if you change the subscripts on the polyatomic, that's not the same polyatomic anymore. Okay. But when you're counting atoms, right, this would have 1 sodium, 1 oxygen, 1 hydrogen, 1 magnesium, 2 nitrogens, and 6 oxygens. That subscript outside the parentheses propagates through the entire unit. for counting purposes. You need to understand that because eventually we're going to use that to calculate the masses of each of these using the periodic table. So we need to know how many of each atom there is in the compound. Okay, I reproduced it here. Notice that some of them occur in regular series. Right? I'll talk about one of them that I prefer, is the one with chlorine and oxygen. So I always start here, chlorine and 3 oxygens with a -1 charge. That is chlorate. If you take away one of the oxygens, you still have a -1 charge. But now you change the ending. Chlorite. Okay. But you can also take away another oxygen and leave it with only 1. But we don't have any more suffixes to cover that change. So we have to use a prefix. This one is hypo. Chloride. Okay. Underneath, hypo, like hypodermic, under the skin. This is under the chloride. And then you can also add one more. So we can go up here, O4 minus, and this needs a prefix, per, chloride, which means 1 greater. Okay, and you can do that with any of the halogens. This could be iodine, so it'd be iodate, iodite, hypoiodide, or periodate. Or you could do it with, let's see, bromine. Right, I'm staying with the halogens right now. So you could say bromate, or perbromate, or bromide, or hypobromite. So once you get that pattern down, you can do all the halogens that way. Fluorine doesn't do that though. It's just chlorine, bromine, and iodine. I hate that way. And there's some others, like, let's see, nitrite and nitrate, or sulfate and sulfite. Sulfite would be SO3 2- instead of SO4 2-. So let's look at one that's a little more complicated than that. Say you have sulfate, right? Ion. And let's say we add a proton to that, a hydrogen. So we add a hydrogen to it. The hydrogen has a +1 charge. So that means this species will be SO4 1-. And you just name it like this: hydrogen, sulfate, ion. These are all ions. Okay. Now, what if we added another hydrogen here? That would neutralize it, wouldn't it? So in that case, you could call it dihydrogen sulfate, which is accurate unless it's dissolved in water. And we're going to get to that when we talk about naming acids. Okay, so really what you need to do is just study this, use it to work problems, and know where to find the information. Remember, one side is sorted by formula, and the other side is sorted by name, alphabetical. So you can use either one. It's duplicated information on both sides. Okay, type 3s. Type 3 compounds are nonmetals with nonmetals. They're always covalently bound, which means they're sharing electrons. So we can't strictly say that it's cation plus anion, right? Because there are no ions; they share electrons. but we're going to use the convention of type 1, type 2 naming convention to help us get started with type 3s. So the help that we're getting is which one comes first. Since they're not ions, which one comes first? Generally speaking, the one that comes first, this doesn't always happen, but the one that comes first is usually to the left, toward the metal side. And the one to the right takes the anion position. And when we name them, the first one is just the element name, just like the others with the metal, just the metal name, just the element name. And then the second one, we use the change to I. Okay, so if we say, before I do that, since they don't have a charge and we can't determine neutrality based upon charge, we just say how many of them there are, how many atoms are in the molecule, because this is a molecular compound. It's not a formula unit like the video described. So if we say we have a carbon and 2 oxygens, the first one occupies the cation position. We just say carbon. And since there's only one of them, we don't use the prefix for the one, which is mono. But for the second one, we do say dioxide. So carbon dioxide is the name for this one. If it were the deadly version of carbon and oxygen, carbon monoxide. We don't say monoxide. Okay. 2 O's together just doesn't sound right. But we still don't say monocarbon. If there's only one in this first position, you never say mono. But you do need to know the Greek prefixes. So are they here on the slide? Yes, they're on the next slide. So that's what you do. You just say how many there are. The trick is deciding which one comes first. In this case, it follows that trend. Carbon is to the left of oxygen in the periodic table. So what are your prefixes? If you don't already have them memorized, we're only going to go up through 10. So these prefixes are mono for 1, di for 2, tri, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8. Everybody knows octane. Octane rating of your gasoline, that's where they get it, octa. And nona and deca is 10. They go way beyond that, but this is where we're going to stop. So we did carbon dioxide. This one will be sulfur hexafluoride. Okay. This one would be dinitrogen tetroxide. Notice we dropped the A. 2 vowels together just don't seem to blend. Chemists can be aesthetic too. All right. So when you're naming a compound, we need a plan of action. So when you see a compound with something here and something there, and then you have so many of them here like that, how do you name it? First thing you do is decide, is it metal, non-metal, or non-metal, non-metal? If it's non-metal, non-metal, you know you go straight to type 3. If it's metal, non-metal, then you have to decide what kind of metal do you have. So you know your periodic table, and you know which ones are fixed charge, and you can decide whether it's type 1 or type 2. Then you carry on with the naming conventions. All right. Let's see. Now, I mentioned earlier the alchemists were pretty good at creating and using mineral acids Well, acids come in lots more flavors than mineral acids. And we need a convention for naming them, but we can't invent it from whole cloth. We've inherited, it's a grandfathered in a lot of the naming conventions for acids. So we just try to standardize them. So what do you need to have to be an acid? Well, we know now that acids always start with hydrogen. Usually 1, 2, or 3 of them, and then something else. Okay? So that something else could be, in this case, chlorine. It could be the chloride ion with a proton. Right? Remember, hydrogens, most hydrogens only have 1 proton and 1 electron. So we're talking about that isotope here has 1 proton and no neutrons. We have the possibility for 1 proton and 2 neutrons for deuterium, and even rarer still is tritium with 2 neutrons. But for the most part, when I say protons, I mean this one. Right? It's missing an electron, the only electron it possesses. So in this case, we will be combining that one with this one. I don't want to muddy the waters too much, but it's really not an ionic compound. But anyway, acids start with hydrogen. Now, the naming convention for this one would be what? It would be type 1 compound. If this were a gas, which it would be if it were not dissolved in water, it would be hydrogen chloride. Right? Fixed charge. This occupies the position of the metal. Actually, this would be a type 3. Hydrogen is kind of off by itself. The only reason we put it on the left-hand side is for balance. This is not really an alkali metal, but we stick it over there just so it's opposite from helium. So actually, that would be a type 3 convention. But if we dissolve it in water, we use the designation here, aqueous, right? Aqueous, dissolved in water. Now its name changes. Now we need the acid naming convention. And the key to naming acids is first ask, does it have a hydrogen out here? And the hydrogen comes first because it's the one that dissociates and combines with water. We'll talk about that in more detail when we get to the chapter on acids. I think that's this semester. We talk about acids. This dissociates, and that's what makes the solution acidic. Right? Sour tasting, in other words. But the next question after you answer that question is there oxygen involved? If there's oxygen, that gives you a different route to naming. If there's no oxygen, then you always start the name with hydro. And then you take hydrogen chloride, the I becomes it. So hydrochloric acid. If there's an oxygen in there, you never say hydro. You only say hydro if there's no oxygen. So let's take another one, the polyatomic ion. How about this one? HCN. Now, if that's not dissolved in water, what would we call it? Hydrogen cyanide. Dissolve it in water, then it's hydro. I becomes ic, cyanic acid. Okay. It's an example of a polyatomic with no oxygen. Now, if you have oxygen, you don't use the hydro. So let's look at an example for that one. Let's say, and of course, if it's got oxygen, more than likely it's going to be a polyatomic anyway. So let's say, oh, we had that original one, the H2SO4. Hydrogen sulfate. Dissolve it in water. Now you take the sulfate, this part, and 8 becomes ick with slight modification. Sulfuric acid. We know that's sulfuric because it was derived from 8. What if it was H2SO3? SO3, this is sulfate, that's sulfite. Right? 8 becomes ick, I becomes us. So this would be sulfurous acid if it were dissolved in water. Now, one that can be confused with this one is one that doesn't have oxygen in it. H2S, dissolved in water. Right? So that one would start with hydro. So sulfide, hydrogen sulfide, would be hydro, I becomes ick, sulfuric acid. So sulfuric acid is this way, hydrosulfuric is that way. I'll put those up there because that's an easy place to get to stumble when you're naming acids. Okay. And that extra credit on naming compounds has several acids in it to give you practice. So here we have no oxygen, no oxygen, no oxygen. Right? So they all start with hydro. Here we have oxygen. So they don't start with hydro. They take the anion part of the molecule and decide what is that. That's nitrate. 8 becomes ick. Nitric acid. And that's all you have to say. It's unambiguous. That's the only thing it could be, except they didn't write the aqueous in here. So we have to forgive them for that. Another possibility, remember when we were doing the homologous series of chlorine and oxygen, polyatomics? This would be HClO2 would be chlorite, right? So ike becomes us, fluorous acid. One of my favorites is this one. Just add a hydrogen here, right? That neutralizes there. Now, what's this? Perchloric. So it'd be perchlorate ion. So it'd be perchloric acid. If it were aqueous, of course. Now that, I've used that in the lab. It's extremely efficient oxidizing agent. In other words, if you want to digest plant material or any living material and extract the ash from it, in other words, the solid components, to analyze them, it will convert all the carbon, all the hydrogen, and all the oxygen to something and blow it off. The problem is it's such a strong oxidizing agent, you have to be careful with it because it reacts so violently with organic matter that if you just put this in organic matter and heat it up, it's likely to blow. So I always tell my class, if you want some real fun, expensive fun, you go to your lab and you take a beaker of concentrated perchloric acid, which is about 70% by weight, and put a nice big pat of butter in it, and put it on your hot plate, and crank the hot plate up to high, pull the sash down, and evacuate the building, because it will blow a massive hole out the side of that building. So how do we use it to make it safe? We used to pre-digest our plant material. We put the plant material in the beakers. We add nitric acid, cold nitric, concentrated nitric acid. Actually, perchloric acid. Nitric is 70%. I'm not sure what perchloric was. I think it was less. It's like 35%. Anyway, we pre-digest overnight. And then you go in the next morning and it would be partially digested. You add your perchloric, then you could crank up the heat and go to town. Okay, naming acids. If you like flow charts, there you go. This came straight out of your textbook, or at least that edition of the textbook. Okay, which one of these is named incorrectly? How are we doing on time? 11:30. What do we go to? 12:30? Oh, 1:20?
The lecture one is at about 30.
Oh, okay. Okay. We're almost done anyway. So how about potassium nitrate? Is that correct? Well, look at your compound. Metal, non-metal, okay. That's the nitrate ion. This is the potassium ion. And potassium is an alkali metal, so it only has one charge. Yeah, that's correct. You only have to say potassium nitrate, and you can write this from the name easily it's unambiguous. How about this one? Titanium and oxygen. Oxygen is -2, correct? So you have -4 total. Titanium is only 1 there, so it has to be +4. So that's wrong. How about this one? Hydroxide. It's always a -1, polyatomic. -4 total. 10 has to be +4. 10 for hydroxide, that's good. Now, when I took chemistry as a student, we had to learn this antiquated way of naming these things. This would be, we use the Latin for 10, stannum, and then that had a suffix on it. So stannic hydroxide would be 4 charge. Stannous hydroxide would be +2 charge. You just have to memorize what each one of those meant. So I'm kind of happy that they went for this route. This is much easier and more methodical. So maybe we're kind of trying to pull ourselves away from the ancient past. So this one, phosphorus and bromine, they're both nonmetals, correct? So we need a type 3 naming convention. Phosphorus, there's only 1 of them, and penta, 5 bromides. That's correct. What about this one? That's a polyatomic. So how do you recognize polyatomics? Well, if you memorize all of them, of course, you'll know that that's a polyatomic. But one clue is there are 3 or more elements and there's an oxygen in there. A lot of the polyatomics have oxygen in it. So that's a clue. It's not definitive, but it's a clue. So you say, okay, CrO4, that's probably a polyatomic, so I'll look it up. And it turns out to be chromate. Now, what's the charge on it? Well, chromate charge is 2-. And calcium is an alkaline earth, which is 2+. Both of them together, you only need 1 of each. So that's correct, calcium chromate. Right, so that's the wrong one. This is a discussion of, there are some compounds that associate with water, but the water is not, it's more strongly bound to the molecule or the formula than, well, it's less strongly bound to the formula than it would be if it were covalent. It's not covalent, but it's stronger than just the weaker interactions like that water would experience as a liquid. And these water molecules exist separately, but they're in the crystal structure. Right? So if you have, in this case, zinc sulfate, and it's got some water in it, it will have a definite proportion of water to the zinc sulfate molecule. And we need a way, a convention for defining that. As it turns out, the zinc sulfate, one of the possible hydrates, we call it, the hydrates of zinc sulfate is 7 waters. There are usually more than one possibilities, but in this case, this is the most common. And how would you write that? Well, you have to say how many waters are associated with 1 unit of zinc sulfate, and we do that here with this dot. It's not a period, it's elevated to the center of the line. And these are called waters of hydration. And you name them first by naming this part of the molecule zinc sulfate, right? Because zinc is a fixed charge, 2+ charge. Zinc sulfate, and then you name how many waters there are. Heptahydrate. That's how you would name a compound with waters of hydration. We do a lab where we actually determine the ratio of water to the compound. Only instead of using zinc sulfate, we use copper sulfate. Okay, that's on the agenda. Okay, that's it. We're done with chapter 2, and then next time we meet, we'll review using the review document.